everybody, to the start of the 2011-2012 School of Informatics and Computing Colloquium Series. We have an exciting set of talks lined up for you for this semester, including some local favorites and some distinguished speakers. And to kick everything off, we actually have somebody who is both, and that is Professor Andrew Hanson, who hardly needs any introduction after being here at IU for 22 years.
Yeah.
And chair of computer science department for 6 of those years. But I'll just mention a couple of things. I think Professor Hanson's first love was physics, and this goes a lot deeper than just his PhD from MIT in theoretical physics. He actually grew up in Los Alamos, downstairs from a couple of Nobel Prize-winning physicists who got their Nobel Prizes for, amongst other things, figuring out how stars burn. And his father and 3 of his uncles were also physics professors.
All 3 of my uncles.
3 of your uncles, all 3 of your uncles. There was not a single uncle who was not a physics professor. And yet somehow he escaped the destiny of being a physics professor. Oh, and I should say one of those 3 is emeritus here at IU. So are there any others who aren't emeritus here at IU? And he pursued his career here in computer science, but maintaining a strong connection, in particular working on computerized visualization of concepts in physics and in astronomy and in mathematics, as we'll be hearing about today. And I also asked him what else would he like more people to know about him, and one thing that he mentioned was jumping into the Atlantic Ocean from the Andrea Doria at 3 a.m. a few hours before it sank into the sea. I'm not sure if we'll get to hear about that today, but I think he wishes more people would ask him about that. So take the opportunity. Andy.
Thank you very much. The work that I have wound up doing over the years, I would like to characterize in broad strokes as trying to make pictures of things that no one has ever seen before. And what I'm going to describe is one of those threads. In particular, there is a path, believe it or not, from Fermat's last theorem through a couple of inroads through very important computer science issues to the visualization of Calabi-Yau spaces, which of course is a very important physics issue. So this is something that has actually occupied me for my entire career at Indiana University, and it's my pleasure today to tell you a little bit about how one can visualize this odyssey. The first element here in the trip is Fermat's last theorem, and some of you may remember 2 weeks ago the Google Doodle commemorated Fermat's 410th birthday with a little thing that showed up and said, "I'm sorry, but I just have discovered a marvelous proof that this doodle is too small to contain." Fermat actually wrote this in the margin of a book in 1637, and it was finally proven in 1985. Superquadrics is a place where the Fermat-like equations entered in several rather amusing ways in computer graphics, actually starting out in 1959 with a competition for a traffic circle design and continuing with a famous paper that I'll describe in 1981. Calabi-Yau spaces started with the conjecture of Calabi in 1954 that there were a particularly interesting class of Einstein spaces. The proof by Shing-Tung Yau, who is now the chairman of the Harvard Mathematics Department, that such solutions actually did exist, and the christening in 1985 by a bunch of string theorists, physicists, of these particular spaces with the name Calabi-Yau. They were not actually called Calabi-Yau spaces before that time. And so what I'm going to talk about is how these things chain together in my mind and what they have in common. What do they have in common? Is it something hard? Is it something sort of hard? Is it something not so hard? Or is it something really easy? What they all have in common is the circle. And what is it about the circle that they have in common? Well, they have in common the fact that the equation of a circle, or circle-like equations, the implicit equation of a circle, is part of the framework. And as anyone in my modeling class will know, there's a particular distinction in the description of shapes, sometimes interesting, sometimes not, between implicit equations, equations which don't necessarily have an obvious solution, and parametric equations, in which, in this case, a one-dimensional object has parametric solutions in the form of the trigonometric functions. So the implicit equation and the parametric solutions of that are something that we will now see repeatedly. So why a circle? Well, Fermat's theorem and the way that Fermat got to looking at Fermat's theorem involves changing the square of the circle equation to any integer power. The superquadrics, which are a shape primitive used in computer graphics and computer vision, perform a map from the parametric solutions of the circle equation to a circle-like equation, not only for any integer power, but for any real power. The Calabi-Yau spaces that may be describing the hidden dimensions of string theory, certain classes of them, there are many, many classes of Calabi-Yau spaces, but certain classes of them are complexified extensions of Fermat's equations. So in some sense, the common thread through all of these is the idea that if you take a circle and you simply sit down and start messing with it and expanding that simple idea, x squared plus y squared equals 1, in every conceivable direction, you can get to places you would never imagine. For all of these things, all we really need to have is a very deep understanding of the circle. Our story begins with Pierre de Fermat, who was born around 1601, we believe, and lived till 1665. And as I say, Google just celebrated his 410th birthday with a Google Doodle on the 17th of August of this year. He was more or less, he was a bureaucrat, kind of an amateur mathematician that did in fact do many interesting things. But the thing for which the popular press, at least, has most remembered him is the 1637 occurrence of his statement of what was actually technically probably a conjecture that we call Fermat's last theorem in his honor, that the equation x to the p plus y to the p equals z to the p has no solutions in positive integers for p greater than 2. If you sit down and you look at that, the more remarkable that statement becomes, because there are lots and lots of integers in the space that that curve can go through, and to have none of them, of those curves pass through an integer is quite remarkable. What he did was Fermat wrote this statement in the margin of a copy of the Arithmetica of Diophantus, essentially a Greek work having a lot of number theoretic aspects to it. And he wrote in the margin that he had a proof, but he never recorded the proof. And in the remaining years of his life, which were many, he never mentioned it again. Nevertheless, after he died, he had a very efficient Boswell, his son, and his son took his annotated copy of the Arithmetica and inserted into the reprinted copy that he published the observations of Pierre de Fermat. And there, in Latin, it is written, "I have a marvelous proof that this margin is too small to contain." So his margin notes were immortalized by his son, who reprinted them in this reprinting Fermat's annotated Diophantus. Finally, beginning in 1993 and concluding in 1995, Princeton mathematician Andrew Wiles and some collaborators who helped in the last pieces actually proved Fermat's theorem using very modern techniques of elliptic curve theory, things that would be completely unknowable by Fermat. And yet, there is still the tantalizing idea that perhaps a more elementary proof exists that Fermat might have been able to know. Keeping all this in mind, I got involved in this whole picture in ways that I will lay out during our journey. Around 1990, at least 5 years before the proof, we made a film called Visualizing Fermat's Last Theorem that actually was shown as an example of mathematical visualization at the first convening of the Visualization Conference, and that actually was followed a year later by the establishment of TVCG, the first Computing Society Visualization Journal. So that the entire field of visualization as an official subfield of computer science actually started literally at the moment that I made this film. So the next time that the things that I got involved with appeared in history was around 1959, or I should say the first time when the things that I got involved in appeared in the history that I know about, is what I might call traffic circles on steroids. The city of Stockholm in 1959 put out a call for proposals for traffic circle shapes. And a Danish poet, believe me, anything can come from a poet, designed a non-circular shape that won the prize, and it basically extended the circle equations by changing p from 2 to 2.5. And so this was a kind of an ovally-like shape that the judging committee for the Stockholm traffic circle liked. And he went on to extend this equation in many ways, including this equation here, which I'll show in a slide or two, is actually an equation for an egg-like object. Examples of these shapes are well known, and in fact, this is a coffee table that I know well, and this is looking at kind of a sideways view, but if you take a straight down view, I'm pretty sure that this is a Fermat equation with power 3. So these shapes were well known even in the 40s and 50s, apparently, to furniture makers for making smoothly shaped furniture that was not so boring as a circle. And this is Pete Hines' super egg, and the feature of the super egg is that because it's not exactly elliptic, it can actually have kind of a little flat derivative on the end, and the super egg stands on its end, unlike most eggs. In computer science, this interesting shape may have actually entered the world first with fonts. Most of you who sat at a computer and scrolled through your font list should remember the name Zapf. So Zapf was a font designer, and it is believed that one of the first occurrences of superquadrics in fonts occurred in Zapf's Melior fonts, all the way back in 1952, actually before the super traffic circle. And if you use Metafont, or are at least aware of LaTeX and Metafont by Donald Knuth, Knuth's computer modern typefaces explicitly contain superquadric shape design options. This is an example of a family of superquadric shapes. If I actually take the circle equation and I use a power 1, I wind up with a diamond shape. Power 2 is the circle, power 3, 4, 5, and so on. And those of you who are familiar with the availability of different norms to measure distances in spaces will recognize these as the equal distance graphs of LP norms. So essentially, superquadrics, in some sense, are closely related to the LP norms. So let me go and do my first little live demo here. Now this is a Mathematica notebook in which I have functions that I can do interesting things. I can make a circle. I can make the Swedish traffic circle 2.5. I can do different powers, and in fact, Mathematica nicely has a little way to take care of this interactively, and so we can actually explore all the shapes that we might get with continuing powers of p. So there's a half. We get up to 1. It gets sort of diamond-like. The diamond moves over. It gets rounder around 2, 3, 4, 5, and it gets squarer and squarer as we go up to the high end. Let's see. What the other thing that's interesting here is that we can actually do a family. So this is I leave everything that's there on as I keep it there, and so there's basically 2, 3, 4, 5. So I think the 3. I think that's the table that I showed you. I think 4 is a little too round for the table, and then it turns out 5 is very important. We'll get to that in a little while, and then as you go farther and farther up, you get closer and closer to an actual square. In fact, I can take the program I used to compute the figure in the notes, and as I go to very high powers, you see it gets more and more square. Okay. So the next thing I can do, and this is where this computer has a little bit of a problem, but I can then change these equations into 3 dimensions. So here is a representation of a 3-dimensional superquadric. I can again change its power to anything that I like. I can go up to more exaggerated shapes. I can build shapes that move that have both a wire frame and a non-wire frame. We can go back to 3. Or up to 5. And these are the shapes as they would appear, sort of generalizations of spheres in 3 dimensions. And then we can actually do this again by making an interactive system that gets us from various shapes to others. We can turn off the faces, see it all in wire frame, and you see what happens in the particular mathematical formula that I'm using. Let's see. Let me look at it straight down like that. You see, as the power gets higher, the locations of the corners get closer and closer to the corners. So that's the map is getting more and more singular, and then when I bring it back, the map gets more and more regular. So that's the live demo of how superquadrics pull together. And so from there, I'll talk for just a minute about the concept of the role of superquadrics in graphics. Actually, I had the pleasure to visit CalTech, where Alan Barr is a professor. He in 1981, many years ago, he introduced the class of superquadric shapes to the computer graphics community in the very first issue of Computer Graphics and Applications, now one of the primary journals of computer graphics. And he did a number of very clever things, and it was my pleasure to have him in the audience when I gave a similar talk at CalTech, so I could bring to his audience the results, the consequences of his interesting work. So what he was doing was the equations that I just showed in the live demonstration were the three-dimensional equations, x to the p plus y to the p plus z to the p equals 1. And he, of course, went much farther than this. He exploited continuously varying exponents, which I did in the software. And actually, there are some very interesting questions involving having light interact with such shapes. And he did some clever tricks involving keeping the equations fixed, but deforming the space around the equations to find the paths of a light ray as they would interact with the surface with essentially zero expense. And actually, in the film that I will show you, there's a very quick mention of this that goes by really fast, but that's what I'm referring to, is some tricks that Barr used in this paper for getting very fast solutions to very complicated light ray trajectory paths. Superquadrics are now part of the general vocabulary. In fact, any of you who might have seen or heard of Pavre, this is a very standard publicly available graphics program for doing a very high quality graphics rendering, and among the primitives that are present in Pavre and other graphics packages are these superquadric shapes. So what Barr did and the exploitation of these shapes as shape models have entered the literature quite directly. I did not originally know anything about Barr's paper. What happened to me is that I was working in the Artificial Intelligence Center at SRI on machine vision problems during the 80s. And a fellow, brand new MIT PhD named Alex Pentland showed up. And he was from MIT, like me, had lots of interesting mathematical ideas. And he started using Barr's paper. So he had read Barr's paper, and he said, well, I can use this for more complicated things. And so he started using Barr's paper for an interactive sketching system. And then he extended that to a shape recognition system in a very well-known paper in the Journal of Computer Vision in 1987. And so it was Pentland, who is now an associate director of the Media Lab at MIT. And he, from the office next to mine, sort of made me aware of Barr's paper, of his super sketch system and superquadrics, and that pretty much was the direct path for me starting to get interested in making pictures of Fermat's last theorem. Here are some of the things that appear as primitives in some of the examples that Pentland put together in SuperSketch, building from a very simple set of primitives, adding some deformation parameters. So this is like a superquadric with a deformation. You can see those characteristic shapes with the rays accumulating at the corners that I just showed you in the live demo. And so he had various ways to pull on the primitive shapes and make them even more complex by deforming them in more subtle ways to make more realistic conditions. And his pièce de la résistance were the logos, which then he circulated as part of the system. This little fellow is named Dino, and this picture here is called The Beach. And we saw a lot of these around SRI while Pentland was working on the SuperSketch system. I still have some fondness for Dino. Why he has a horn? I think there was a song, wasn't there? Anyway. So from 1987, when Pentland started working on that, through 1989, which is when I left SRI and came to Indiana University, I sort of got the idea that one might take these shapes and try to do some mathematics, or at least some very top-level mathematics with them. And so I started working on this. This is basically right around then, between like 1980, 85, 88, 1990, 1994 was sort of a golden age of mathematical visualization. And the first visualization conference was held in 1990 in San Francisco. And so the film that I made was shown first at the visualization conference, and then at CGRAPH, the big ACM computer graphics conference. So when I first got involved, the first thing I did is I got involved in superquadrics from Pentland, and you could see right away, if you happen to be thinking about Fermat's theorem, that the equations looked a lot like Fermat's equations. And one of the ways that you can recast this is if it's x to the p plus y to the p equals z to the p, then you can divide by z, and instead of having no integer solutions, what you have is no rational solutions according to Fermat's theorem for integer p greater than 2. So when I got here, this was actually right away in the fall of 1989 when I first arrived at IU. John Ewing was the chair of the math department, and I knew people who knew Chuck Livingston. And I started talking to them about whether I could do something, anything, using computer graphics, which was my emerging specialty, to think about Fermat's theorem. And I think it was John Ewing first, and then later Chuck gave me a lot of help on the concept of turning this into a complex equation, a complexified equation. So instead of being a curve, it turns into a surface. Instead of being a curve in 2D space, it turns into a surface in 4D space. And this was long, long before I knew anything about Calabi-Yau spaces. And this was all concerned with trying to do something with Fermat's theorem. So now I'll show you the video. I might turn the lights down a bit for this one. And the one thing I have to say, this is a 3-minute video. This is not a long, drawn-out video. But there were time limits on the films that you could submit to the animation theater. And so this goes by really fast. And I remind you again, this was done, of course, way before the theorem was proven. Video lighting.
In the margin of an ancient book, the 17th century mathematician Fermat stated that the equation x to the n plus y to the n equals z to the n cannot be solved with non-zero integers x, y, z for any integer power n greater than 2, and then wrote, "I have discovered a truly marvelous proof that this margin is too small to contain." The statement remains unproven to this day. Computer graphics can help us visualize the nature of mathematical ideas like Fermat's theorem. Fermat's equation itself is just a cone for n equals 2, and there are many integers, such as x equals 3, y equals 4, and z equals 5, that satisfy the n equal 2 equation. If we vary n continuously, the cone changes to an inverted pyramid. The slices at constant z are two-dimensional superquadrics with exponent n. Varying n smoothly interpolates between circles and squares. The curve passes through many integers as n varies, but somehow just misses hitting any integers for integer values of n, unless n equals 2, the perfect circle. Just as one can ray trace a deformed solid by following a deformed ray through the undeformed shape, we can deform the integer grid instead of the Fermat curve. Recent attempts to understand Fermat's last theorem have explored the relationships between number theory and the algebraic geometry of surfaces. Instead of looking for intersections of a cone with a 3D grid of integers, we look for intersections of a real 2D curve with points whose coordinates are ratios of integers. In this framework, Fermat's equation extends to a two-dimensional surface embedded in the four-dimensional space called CP2, the complex projective space of two complex or four real dimensions. For each n, the surface becomes a patchwork quilt of n-squared pieces that surround the origin and extend to infinity in two complex dimensions. To visualize what is happening inside the surface, we can sweep the surface out from the outside in, or cut into the inside, or use transparent displays. For each integer power n of Fermat's equation, the surfaces have the topology of spheres with more and more teapot-like handles. To see these as the closed surfaces they really are, we transform the surface so it lies within a compact sphere. The clearer our mental picture of the problem becomes, the more likely it is that we will gain intuitive insights that will finally allow us to solve the problem. In fact, wait, I think I see a way to prove the theorem. Yes, I can prove it, but the proof is a bit long. Now, if only I could explain it to you before I run out of videotape.
Okay, so that's the Fermat video. And give me a second to clean up here. Get ready for the next one. And back to the talk. Okay, so that was the that was what we did in 1990, and as the availability of those images became better known, we had lots of publicity. And so, for example, the cover of Science News then had this image. And in fact, one of the things included in there, so just to tell the story, at the SIGGRAPH conference at a reception, I ran into this guy I didn't know named Stuart Dixon, who was an artist interested in mathematical objects. And so I corresponded with him and provided the equations to him, and that led to this cover story in Science News. And a few months later, he sent me this. So this is an actual physical artifact of the power 3 Fermat equation. He did quite a few of those. He told me this was actually worth $1,000 at the time. It was done at Hughes Aircraft, and he had a friend who would do these for the purpose of doing art. But if you had actually gone to Hughes Aircraft and tried to get this made, it would have cost you $1,000 in 1991. So Stuart did a lot of work on artistic uses of the equations that we used in the film and in the visualization conference paper. And then I and some other mathematical visualizers wrote a feature article in the July 1994 issue of IEEE Computer, and we got the cover picture. So we actually got the cover picture of IEEE Computer. And if any of you have tried to get your article on the cover of IEEE Computer, you know that's not easy. Quite a number of other things appeared in that year, including the American Mathematical Society published a bunch of things which had Fermat shapes as little side interest articles, because in 1993 it had already become known that Andrew Wiles was converging on proving the theorem. And so these and a number of other things, including Science Magazine and Scientific American, used these images to illustrate articles about Fermat's last theorem. So next, I'm sitting at my desk. Out of the clear blue sky, I get a phone call from a physicist I had never heard of in my life named Brian Greene. He had someone point out these Fermat surface depictions, and he wanted to know if there was a way that those could be used as figures illustrating Calabi-Yau spaces in a book he was writing on string theory called The Elegant Universe. And this actually became a top-selling popular science book between about 1999 and 2002. And he has become quite a celebrity. And anyway, his suggestion it turned out there was one thing I hadn't done. And so he suggested the thing I would need to do to actually do what he needed, and it all worked. And this all became part of what is now a rather large body of visualizations and images on Calabi-Yau spaces. So just for a quick overview, what is a Calabi-Yau space? What was Brian Greene interested in? What are the string theorists interested in? Well, a Calabi-Yau space is a particular n-complex dimensional manifold which has a very interesting property that it has a vanishing Ricci tensor. Vanishing Ricci tensor, for mathematicians, is just a vanishing Ricci tensor. For physicists, a vanishing Ricci tensor is a vacuum Einstein equation. So what was interesting was the link between the existence of these equations and the solutions in particular circumstances to vacuum Einstein equations. It turns out that the fifth power, the quintic complex Fermat surface, p equals 5, will provide the 10-dimensional string theory with the 6-dimensional Einstein manifold needed for the missing dimensions of space-time. That is where the interest comes from. And so although there are more advanced versions of string theory that work in 11 dimensions, referring to the basic string theory with 10-dimensional space-time, since we only see 4 dimensions, 3 dimensions in space and 1 in time, there have to be 10 minus 4 or 6 remaining dimensions, and the Calabi-Yau quintic polynomial works as one of a number of alternatives. In fact, a very, very large number of alternatives. This is simply the simplest and the most photogenic, I would say. The mathematical part of the interest in Calabi-Yau spaces actually has to do with the fact that this started with Calabi's conjecture and Yau's proof that Calabi-Yau spaces with Ricci-flat metrics exist, but so far, no one has ever written one down. They exist. There is no example. It's a major unsolved problem in mathematics to make the connection between Yau's proof, for which he's now chairman of the math department at Harvard, and the question of, can we write one down? Physicists, I guess, are the ones who want to write it down. Mathematicians are happy to have an existence proof. But me as a visualizer, I would like to see these things. So if you can't write it down, maybe making a picture would help. And so that's part of this whole process is let's make a picture. So here is the picture. This is basically what you have here in hard copy. This is a much later version which actually allows color instead of just plastic. And this is the Calabi-Yau quintic. And I'll show you in the live demo in a couple of minutes the amazing things that you can learn simply from the way I chose to draw this as opposed to some other ways that you might choose to draw this shape. Of course, there are 6 hidden dimensions in the Calabi-Yau space. This is a 2-dimensional surface. This is a cross-section. This is a slice through the 6-dimensional surface, since that's what I can draw. In Greene's book, after we got in touch and I started sending him things, his artist essentially took what I sent and turned the simple example of a Calabi-Yau space into this picture in the book. And then the idea was, if I have an object that is 3-dimensional and it has a 4th dimension, I can imagine the 4th dimension as occurring in snapshots. So time 1, time 2, time 3, times 4, times 5. So that turns a 3-dimensional object into a 4-dimensional object. So this is basically adding 2 dimensions to the 2-dimensional object. He actually he needs 2 more. This isn't quite enough. But the reason why in this picture and in the pieces of film I'll show you, these are laid out as copies, is trying to give the idea that these are copies that extend the 2-dimensional surface to a full 6-dimensional manifold. This is really a representation of a 4-dimensional manifold. There need to be two more dimensions. And then he wrote another book a couple years later, The Fabric of the Cosmos. And in that book, they took what you can see is this color image, and then somebody went in with Photoshop and put complete nonsense spider webs on it, absolutely meaningless. It's like, okay, I know you want to see something here, but what is it? There are lines in the Calabi-Yau space images that I create that do mean something, but not these. Among the ways you can deal with this in a way that have meaningful lines, this amazing sculpture of Bathsheba, and I know at least one person in the audience tells me that he actually went online and bought one of these for himself. This is, believe me, she's an amazing artist. She has many things besides this. She has galaxies and all kinds of things all put into glass spheres. But she did this for me. I gave the first copy of this in person to Brian Greene when I got the first copy hot off the presses. But this is, in my opinion, this is one of the most beautiful shapes or representations, actually, of this shape I have ever seen. Come take a look at it. Now, what happened next after, since Greene became sort of a spokesperson for popularizing string theory, he then was chosen to be the narrator of a 3-part NOVA series on string theory. And the NOVA team contacted me, and I sent code to their professional animation team in London, and they made a 3D Studio Max plugin. And from their 3D Studio Max plugin, they generated a whole set of images that were used in the background of the NOVA series and actually appeared that same month on the cover of Scientific American. So you can see I've had quite a series of magazine covers over the years. So here's a typical picture that the art design team for NOVA made from my original equations, and then they did this version of that, attempting to show the multiple dimension. And with some luck here, I will be able to show you some of these.
Extra dimensions.
Let me
literally mean extra dimensions of space that are
these tiny extra dimensions curled up into such peculiar shapes have any effect on our everyday world.
If string theory is right, we would have to admit that there are really more dimensions out there. And I find that completely mind-blowing.
So this is the series of images that went into the background describing in all the parts of the narrative in the NOVA series. And so these were based on the equations that I provided to that particular team. So having seen all this, I pose for you, since this is, after all, an informatics and computing lecture, what's going on here? You know, what is the context of what you're seeing on the screen? Is this art or is this science? Well, the honest answer is it's a bit of both, but there is a distinction between the goals of the NOVA animators and the images that appear to have been chosen for Greene's books and my standard images that I tend to prefer to distribute to people when they ask for a copy of one of these images. And there is a very standard and simple scientific way of looking at this, something a physicist, a biologist, and truly computer visualizers need to consider, and that is falsifiability. You do not have a scientific theory, you do not have a scientific representation unless you can tell if it's wrong. So with my representation, in particular with this type of a representation, what you can see is the degree of the polynomial. There's a, let's see, I'll just pop back and look at this one. the fact that there are 5 pie slices tells you, if you know how the surface was constructed, instantly that the degree is 5. And the construction, the colors actually tell you what part of the patchwork quilt of the object you are in. In other words, if it were wrong, you could actually tell that it was wrong based on the fact that some part of that pie slice would appear incorrectly. So in my opinion, when I create something that I am satisfied with as a visualization, it will often be quite different from those writhing purple tulips that you saw in the Nova animations, because in fact there is a criterion, that is falsifiability, that can distinguish a visualization from something which is simply art. So I promised you at the very beginning that I would make the equation of a circle into a story that took us all the way to the end to Calabi-Yau spaces. So I've not done very much complicated mathematics. I have 2 slides. And in these 2 slides, if you are awake, I will fulfill my promise. How did what I just showed you relate to the equation of a circle? Well, here goes. How to write down a Calabi-Yau space image. I start with an equation of a polynomial in complex variables. I can do it in n dimensions, actually, any dimension that you want, where I pick a power and I take a homogeneous polynomial of degree p and I set it equal to 1 with n complex variables. I actually published this in the notices of the American Math Society in 1994. This was actually quite a bit after the 1989-1990 creation of the film. But the whole method is based completely on Barr's superquadric trick. And in Barr's original paper on the creation of superquadrics for graphics, he extended the equation of a circle to the equation z1 to the p plus z2 to the p equals 1 for any p by simply substituting z1 equals x to the 2 over p, z2 equals y to the 2 over p. If I plug this into this equation, the p's cancel out. I get x squared plus y squared equals 1, and it's solved by cosine theta and sine theta, even for complex angles. So what you do is, and this actually took us, my first very excellent graduate student and I spent a considerable time, including working with some of my mathematician friends across the sidewalk. And finally we realized that you have to allow only the first quadrant, only the real quadrant of sine and cosine, and then for the real part, and then you let the imaginary part of the angle vary as much as you want. Those define a little 2-dimensional patch of z1 and z2, and then each of those patches extends further into complex space by a pair of p labels. So with a pair of p labels, you have a total number of labels, k1, k2, p squared, and you just multiply by phase. Use an integer from 0 to p minus 1 as the phase. This gives p squared patches that fit together. And what you see here, actually the blue in the background is the first patch, the 0 to pi over 2, and the red says that this is the very highest amount of the k1 phase. The brightest green is the highest amount of the k2 phase. I can tell each of the 25 patches by its color. I can tell you exactly how they fit in around the pi slices. But this is only a part of the story, because there is a more complicated piece of the story that I'm only this year going ahead to finish out and fill in the details of, and that is that the true space in which this object lives is called CP2, complex projective 2 space. And what is drawn here is a little corner, a local corner of Euclidean complex space, 2 complex dimensions, not CP2, just C2. CP2 bends around and closes up. So there's a more complicated way to represent the equation so that these little edges that stick out and actually go out to infinity here curl back around and close up like that. And this is actually something, part of a long-term program I'm, again, working on with a friend, Jiping Shah, faculty in the mathematics department. And this is actually even a more accurate representation of this because the two-dimensional cross-section of the Calabi-Yau quintic should have genus 6. It should be like a sphere with 6 holes in it. And that is hard to see here, but much harder to see here because you aren't seeing the correct compact definition. You can see a little more by looking into the middle of it. This is a wireframe representation, but this is, in effect, this would be the next generation of Calabi-Yau space pictures. So let me do a quick live demo here. So this is the power 2. This is z1 squared plus z2 squared. So you can see the circle. You can just see x squared plus y squared equals z squared. That's the real cross section I'm looking at here, and I can rotate this in 4 dimensions. And so this is a complete description of the power 2. The power 3 is actually quite remarkable. The power 3, you can look at it again from the side, and you should be able to see this is the cubic. There's the cubic curve. So this is z1 cubed plus z2 cubed, complexified, and the most interesting thing for me about this particular representation is that you can see that the complex planes, z1 and z2 equals 0, cut through the center point of the pi. So the center point of the pi slices is the fixed point of the complex transformations, and that basically gives you a very nice visualization as I rotate the whole object in 4 dimensions of what it means to lie in the z1 equals 0 plane or the z2 equals 0 plane for this surface. And then finally, this, for you mathematicians in the audience, this is the quartic. This is the cross-section of the K3 manifold. You can see again from the 4 pi slices, it's the quartic. And then finally, our old favorite, the Calabi-Yau quintic. And there's the Calabi-Yau quintic. Okay, so this is a body of interactive 4-dimensional visualization software that was developed by myself and my graduate students specifically for the purpose of displaying these local representations of polynomials in complex projective spaces. Now, I have one more little surprise for you, which is that this is not the end. This is not the whole story. There is actually more. There's another story. And give me just a second. This is a 4-dimensional rotation system driven by the iPhone, an application that is now available free on the web. This is actually a 4-dimensional die, it turns out, and I can do things like I can actually roll the die and make different sides of the face come up. But that's not all I can do. In the desktop version, not the version that's released to the web, I can actually control the Calabi-Yau space in 4 dimensions from any place in the room. So there is the 4-dimensional rotations of the Calabi-Yau space, and I believe right at the moment we're getting a kind of slow response on the network. Sometimes this room gives me response, and sometimes it does not. Anyway, so there you are. So this is the remote control version of the 4-dice iPhone app. I invite you to try the 4-dice iPhone app as well. So That was the name of the app is 4DICE. There it is on the board. And that's basically what the iPhone application looks like. It's essentially a hypercube visualizer, but it would be a whole separate lecture to tell you how to do with it. Okay, so that's the story of my journey through the world of mathematics, starting with the circle, ending up with Calabi-Yau images that you can control from an iPhone any place across the world. I could actually log onto that computer from France and control that image. It's been an interesting journey for me, going from superquadrics and my office neighbor at SRI all the way to Indiana University over the last 20 years when I've actually been working on this. I'm happy to have had the opportunity. But this is still going on. So just last spring, or last fall, Yau wrote his own book of his own story of how he got involved with the geometry of the universe's hidden dimension, and I did his cover. That's my artwork for his cover. And the chairman of the Stanford Math Department called me this spring and said, he's coming to give a talk on his book. Quick, get me a poster. And so I made another image for that. Actually, there's a member of the Wolfram research staff, the makers of Mathematica, over in Urbana, named Jeff Bryant. And Jeff Bryant has put together some of my old Mathematica code to make a nice interactive system. And a graduate student of Gordy Kane's, some of you who are physicists may know who Gordy Kane is. So a graduate student of Gordy Kane used Jeff Bryant's adaptation of my code to make this picture, which showed up on the cover of just this last November, Physics Today. And a reprint of that article with some modifications showed up just 2 weeks ago in Parody, the Japanese version of Physics Today. And the other thing that shows up here is actually this thing has become an icon. And so who knew that Calabi-Yau spaces and string theory would become a T-shirt? So this is supposed to be, this is a Calabi-Yau space, of course, so it's I heart string theory, but with a Calabi-Yau space instead of a heart. Not only that, but where did this show up? This showed up, they actually contacted me while I was on sabbatical in Cambridge from the London advertising system, and this object, I don't know if you can read it, but it says smart but casual. And they had Maxwell's equations, and they had Darwin, and they had I heart string theory. These were all over London, advertising a line of jackets and clothing with a, quote, smart T-shirt under the jacket. And this was an example of the smart T-shirt. So as you can tell, this has been a huge amount of fun. I've enjoyed every minute of it. I've got a lot of interesting pictures that have appeared. From circles to superquadrics, from superquadrics to Fermat surfaces, and finally to Calabi-Yau quintics. Can we see the hidden dimensions of string theory? Maybe, maybe not. There's still more to do. So I'd like to thank a lot of people, including many of my graduate students, Xiaoqi Yan, who visited this summer and actually implemented 4Dice. I'll leave this up for a few minutes. These are the web pages. The 4Dice apps. 4Dice is on the YouTube, a video corresponding to that, and the Fermat video that you just saw, I just put up on YouTube a couple days ago. Thank you for listening. Questions? Yes.
So, how did these sort visualization would help you, for example, to classify topology. Just use this to have characterization of topological environments, say that.
Okay. The topological features of Calabi-Yau spaces are extremely well understood just from algebra. So there's nothing that I can do, because I already have the algebraic equations before I make the picture. And so unless they were very unusual equations for some reason, you could already tell the topology from much simpler calculations than actually making the picture. Yes?
So has it been cases of the visualization resulting in mathematical insight that was used to make programs?
Let's just say the jury is out on that, because that is actually an element of my ongoing research. You never know what's going to help, because what you need is the circumstance where you have an idea in your head and you're out running in the park, and then something goes, oh yeah, it might go that way. And any kind of intuitive picture, any kind of qualitative information might take you, in the jump from one piece of quantitative understanding to another piece of quantitative understanding across a qualitative leap. So I don't have a really good example. I wish I did. I'm working on it.
My second question, what happens when you turn the accelerometer on?
Oh, okay. That's okay. So the accelerometer works in on the iPhone, and so I didn't go into the details of the four-dimensional control, but essentially you pull the object in the X direction or the Y direction or the Z direction, and when you're just on the screen with your fingers, you have to do a special thing to move in the Z direction, but I can attach the motion, the 3D motion of the iPhone to the accelerometer to tell me which direction it's moving, and then move freely and completely explore the four-dimensional space by just moving my hand around in space.
So my 4 dice isn't working. Can you help me?
There's actually a help file. No, but there is actually I wrote a whole little article there.
Seriously, no. This may be a naive question, but nobody's written down the equations for the analysis, right?
Okay, I'll clarify that just to make sure you got it right. Okay, so the equations for topological Calabi-Yau spaces are what I'm using. So the quintic is known to give something which is topologically perfect. It is exactly the topology of a Calabi-Yau space. However, the induced metric of that embedding is very, very far from Einstein, nowhere close to Einstein. And what is not known is how to take that topological space, which I can make a picture of right in front of your eyes, and put a metric on it, which is Einstein. That explicit, Yau got his prize-winning work for proving that an Einstein metric exists on that topology, but no one has written down the metric.
So then the falsifiability point that you made a bit later is just with respect to the relationship to the image and the actual equation.
And the topology. And the topology. Yes. Well, thank you very much. Appreciate it.